This is Spacetime Series 25, Episode 39, for broadcast on the 1st of April 2022. Coming up on Spacetime, new properties discovered in hybrid Matter-Antimatter Helium, new studies suggest the oceans of Enceladus are boiling, and OneWeb switches from Soyuz to SpaceX. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
Physicists at CERN have discovered new properties in hybrid Matter-Antimatter Helium. The hybrid Matter-Antimatter Helium atom contains an antiproton, that is an antimatter equivalent of the proton, in place of one of its two electrons. But now researchers have found an unexpected response to laser light when these artificially produced atoms are immersed in superfluid helium. The findings, reported in the journal Nature, opens new areas of research looking at the differences between matter and antimatter and physics beyond the standard model, in particular condensed matter physics and perhaps even astrophysics. There are 9 known isotopes of helium, but only helium-3 and helium-4 are stable. In Earth's atmosphere, there are 1 million helium-4 atoms for every 1 helium-3 atom. Helium-4 consists of 2 protons and 2 neutrons, whereas helium-3 is composed of 2 protons and just a single neutron. And other than protium, which is ordinary hydrogen, helium-3 is the only stable isotope of any element in which there are more protons than neutrons. Scientists use hybrid matter-antimatter helium atoms to determine the antiproton's mass and compare it with that of the proton. These hybrid atoms contain an antiproton and an electron around the helium nucleus, and are made by mixing antiprotons produced at CERN's antimatter factory with a helium gas that has a low atomic density and is kept at low temperatures. Low gas densities and temperatures have played a key role in these antimatter studies, which involves measuring the response of hybrid atoms to laser light in order to determine their light spectrum. High gas densities and temperatures result in spectral lines caused by the transition of antiprotons or electrons between energy levels that are simply too broad or even obscured to allow the mass of the antiproton, relative to that of the electron, to be determined. This is why it came as a surprise to researchers when they used liquid helium in their study, which has a much higher density than gaseous helium, and discovered a decrease in the width of the antiproton spectral lines. Moreover, when they decreased the temperature of the liquid helium to values below the temperature where it became a superfluid and can therefore flow without any resistance, they found an abrupt further narrowing of the spectral lines. The study's lead author, Anna Sota from ETHC, says this behavior was completely unexpected. The optical response of the hybrid helium atom in superfluid helium is starkly different to that of the same hybrid atom in high-density gaseous helium, as well as that of many normal atoms in liquids or superfluids. Right now, the authors think the surprising behavior could be linked to the radius of the electronic orbital, that is, the distance from the nucleus at which the hybrid helium atom's electron is located. In contrast to that of many normal atoms, the radius of the hybrid atom's electronic orbital changes very little when laser light shone on the atom, and so doesn't affect the spectral lines even when the atom is immersed in superfluid helium. However, further studies will be needed to confirm this hypothesis. The findings have several interesting ramifications. Firstly, researchers are looking at creating other hybrid helium atoms, such as pionic helium atoms, in superfluid helium using different antimatter and exotic particles in order to study their response to laser light in detail and measure the particle masses. The substantial narrowing of the lines in superfluid helium also suggests that hybrid helium atoms could be used to study this form of matter and potentially other condensed matter phases. And finally, the narrow spectral lines could in principle at least be used to search for cosmic antiprotons and antideuteroids, a nucleus made of an antiproton and an antineutron of especially low velocity that hit the liquid superfluid helium that's used to cool experiments in space or in high-altitude balloons. Masaaki Hori is one of the scientists involved in the study.
You know that in the beginning of the universe, there was a big explosion called the Big Bang. And what CERN does is to try to recreate that Big Bang. And Einstein has shown us that the early universe was filled with energy. That energy can be converted into matter. So this was originally energy. But when we try to recreate the early universe inside the CERN accelerator facilities, we discover a very interesting fact. When you convert energy into matter, you always produce the equal amount of antimatter. This is unavoidable. It is fundamentally built into the universe. So welcome to the Asakusa experiment at CERN's antiproton decelerator facility. The experiment Asakusa is an international collaboration that studies an atom made of half matter and half antimatter. There's a helium nucleus around which there are two electrons. In our experiment, we replace one of these electrons with an antiproton. So we synthesize an atom with a helium nucleus at the center, with an electron and an antiproton revolving around it. And in the past, we studied the mass of the antiproton and compared it with the mass of the electron to study the symmetry between antimatter and matter. That is the main goal of our experiment. But when we tried to do this, we discovered a surprising, unexpected phenomenon. Helium, when you cool it down, it will become a liquid. And even if you cool it down to 2 degrees above zero, it turns into a superfluid. We stop antiprotons in the superfluid so that this half matter, half antimatter atom is created inside the superfluid liquid. Then we shone a laser beam through the transparent liquid, and then we found that the atoms inside this liquid is behaving almost as if it's not being disturbed by the surrounding matter around it. This was very surprising for us because in the past we always took care to keep the atoms away from matter. It's as if inside this liquid, the antimatter atom perhaps is sitting inside a bubble, a protected bubble of an electron, so that it can be trapped inside liquid and studied. So this was the surprising effect. We think this can be useful for several applications. One is that the antiproton can be a kind of probe, a measurement device to study the behavior of the condensed superfluid liquid. That is one possibility. A second possibility is in the space probes in outer space, there is also liquid helium. And now we must assume that since there are antiprotons in space that are flying toward the Earth, some of these antiprotons will stop inside the liquid, which is already in space, and producing these atoms. And then if you can put some kind of measurement device into space, you can study the properties of the antiprotons that are coming from space. That is a second possibility. A third possibility is that there are many types of different antimatter in the universe, in the standard model. There are things called pions, which are negatively charged, kaons, which are negatively charged, antideutrons, which are negatively charged. You can, in principle, put all of these particles also into liquid and study their properties in that way. We hope this new finding will open new doors into this kind of applications.
That's Masaaki Hori from CERN. And this is Space Time. Still to come. New studies suggest Enceladus' oceans are boiling, and OneWeb switches from Soyuz to SpaceX. All that and more still to come on Space Time. A new study claims the famous South Pole tiger stripe fissures on the Saturnian ice moon Enceladus are being created by seawater pressure due to expanding ice. However, the new findings reported in the journal Geophysical Research Letters still can't explain the geysers, which erupt from the cracks, sending water high into space. Back in 2006, NASA's Cassini spacecraft discovered curtains of water spraying out from these tiger stripes. Observations found as much as 200 kilograms of water per second was being ejected into space. The South Pole tiger stripes are located at one of the thinnest points in the 20 to 30 kilometre thick icy crust, which completely covers the 504 kilometre wide moon. Enceladus has a global subsurface liquid water ocean beneath its icy sheets. The water is kept liquid by frictional heat generated by gravitational tidal forces produced as the tiny moon stretched and crushed as it orbits Saturn. The new study suggests that expanding ice during millennia-long cooling cycles could sometimes crack the moon's icy shell, allowing the oceans to seep through as continuous cryovolcanism. The study's lead author, Max Rudolph from the University of California, Davis, says computer modeling shows cracks from the surface could reach all the way down to the subsurface ocean, causing the eruptions. The model accounts for cycles of warming and cooling that lasts on a scale of 100 million years, associated with changes in Enceladus' orbit around Saturn. During each cycle, the ice shell undergoes alternate periods of thinning and thickening. Rudolph says the thickening happens as water freezes at the base of the ice sheet, which grows downwards like ice in a lake. And this increases pressure on the water below because ice takes up more volume than liquid water. The increasing pressure also generates stress in the ice, causing fissures and allowing liquid water through. But the study also found that the pressure could never be large enough to squeeze the liquid water all the way up to the surface and create the geysers. Rudolph points out Enceladus lacks an atmosphere, so the geysers are best explained by an earlier hypothesis suggesting that the water in the crack spontaneously boils as it reaches the surface and is exposed to the vacuum of space. The same thing happens with comets. He says that hypothesis is further supported by the lack of any evidence for cryolava flows leaking from the cracks onto the moon's surface. Meanwhile, there's growing evidence that Jupiter's ice moon Europa, another frozen world with a global subsurface liquid water ocean, may also have similar eruptions, although less is known about the activity going on there. But Rudolph says this mechanism of ocean pressure and spontaneous eruption can't explain the cryovolcanism that's been happening on Europa. And that's where NASA's Europa Clipper mission comes in. It's slated for launch in 2024 and may well help answer those questions. This is Space Time. Still to come, OneWeb switches from Soyuz to SpaceX. And later in the science report, discovery of a fabric that can literally hear sounds. All that and more still to come on Space Time. Broadband internet satellite operator OneWeb has dumped the Russian Soyuz launcher in favour of SpaceX's Falcon 9 after Russia refused to launch a rocket containing 36 OneWeb satellites. The Soyuz 21B, equipped with a frigate upper stage, was already on the launch pad at the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan, ready to carry the OneWeb satellites into space. But Moscow decided to scrub the mission in response to the European Space Agency's sanctions against Russia in the wake of Vladimir Putin's invasion of Ukraine. OneWeb had undertaken all 13 of its previous launches using Soyuz, successfully placing all 428 of its 150-kilogram satellites into orbit. OneWeb are planning an initial constellation of 648 satellites in 12 near-polar orbital planes at altitudes of 1,200 kilometers. Arianespace and OneWeb have been working with the Russian Federal Space Agency Roscosmos for nearly 2 decades, and Roscosmos was under a contract to carry out 16 Soyuz launches for OneWeb between December 2020 and the end of 2022 to launch the company's satellites. However, Russia suspended cooperation with ESA and halted all launches from the European Space Agency's Kourou spaceport in French Guiana, withdrawing its 87 technical personnel stationed there in response to the European Union sanctions over Moscow's invasion of Ukraine. This is Space Time. And time now to take another look at some of the other stories making news in science this week with the Science Report. Planet Earth's poles are continuing to get warmer, with new studies showing parts of Antarctica are now more than 40 degrees Celsius above average, while areas of the Arctic are over 30 degrees Celsius warmer. Last week, weather stations in Antarctica smashed records, with Concordia Station, which is located at an altitude of 3,234 metres above sea level, hitting an all-time high of minus 12.2 degrees Celsius. Meanwhile, the Terra Nova Base Station on the Antarctic coast was in positive territory, reaching a balmy 7 degrees Celsius. Even one of the very coldest places on Earth, Antarctica's Dome Sea, is now recording temperatures of minus 10 degrees Celsius, compared to the minus 43 degrees Celsius it should be seeing this time of year. Weather models by NOAA, the American National Oceanographic and Atmospheric Administration, show the Antarctic continent as a whole is now some 4.8 degrees Celsius warmer than its baseline temperature between 1979 and the year 2000. At the same time, the Arctic as a whole was 3.3 degrees warmer than its 1979 to 2000 average. And the Earth as a whole is now 3 degrees Celsius warmer than its 20th century average. A new study warns that teens who spend more of their free time online are more likely to have higher levels of stress and more feelings of sadness and suicidal thoughts. The findings, reported in the journal PLOS ONE, are based on a study of nearly 30,000 high school students. Researchers specifically looked at non-academic time being spent online. They found that students with lower internet usage appeared better off on a range of measures, including better health, reduced stress, fewer feelings of sadness, and fewer suicidal thoughts, compared to groups with higher internet usage. Scientists have developed a new type of fabric that can quite literally hear sounds. They say the fabric could one day be used for a range of health and security measures. A report of the journal Nature claims the new design uses an electrical material called a piezoelectric fibre, which is woven into fabric yarns. Using a similar mechanism to that of the human ear, the authors say it can convert pressure waves at audible frequencies into mechanical vibrations, which can then be processed into electrical signals. The machine-washable fabric can detect the direction of clapping sounds, facilitate two-way communications, and monitor heartbeat. Researchers say the heart monitoring could eventually assist in health monitoring efforts, while directional listening ability could help the hearing impaired, and it would also have security potential, like detecting the direction of a gunshot. Scientists at Caltech, the California Institute of Technology, have taken on the serious scientific study of working out how to really scare people. The haunted house experience, as it's been called, was developed by a research team to reveal insights into the body's reaction to threats. Tim Mendham from Australian Skeptics says while it didn't really come up with anything new, it's probably nice to have the numbers based on an intensive immersive live-action threat environment.
Yeah, it's great to actually sort of wire people up and to see their reactions to a situation of fright. What the scientists at Caltech, which is not an insignificant sort of place for science, did was they got a whole lot of volunteers and they wired them up to see what their reaction was. And I think from an interesting point of view, it stops there. What happens is the conclusions they reach. They basically walk these people through, like a walk-through ghost train. These researchers decided to wire all these people, volunteers up, and they walked them through a series of 17 rooms, obviously with different sorts of scary bits in them. And what they discovered was quite fascinating, is that there's more scares when you've got more people in the room, that unexpected scares produce a higher response. And there's more frequent responses make people feel more afraid. And you think, Well, you have a bunch of people in the room all going screaming like that, and that makes it screamier. And someone leaps out of you unexpectedly, and it produces a higher level of response. And that the more you are scared, the more you will be scared. And I really could have saved them the effort of building these 17 rooms and told them, yep, that's the way it's going to work out. So sometimes you've got to wonder about the science. It's nice for them to do a test and it's nice for them to get the results that are sort of stating the bleeding obvious, basically. Other things they say, when someone gets really scared in the first room, but they're by themselves, you have a lot of scares in the first room, they tend to get less scared by the reach the end because they're basically being over-scared. But if you've got a lot of people in the room, you can feed off each other, therefore you get more scared. So they went to a lot of work building 17 rooms, wiring everybody up, and therefore writing a paper about it and saying, look what we've done. And the summary is just ho-hum, quite frankly.
That's what blue sky science is all about. Sometimes it doesn't pay off.
They could have taken people to the movies and got exactly the same result, right? When you get a lot of people in a theatre screaming, it's scarier. When you get the shock horror, someone jumping out of the darkness, it's scarier than someone just wandering around, although Hitchcock managed to improve on that system quite a lot. And when you get a lot of shocks, you're in a heightened state. But seriously, they could have spent $15, go to the movies, go to a Halloween film or something like that, and they would have got exactly the same result. They didn't have to build 17 rooms and wire people up and make it look all scientific. Quite frankly, sometimes you look at scientific papers and you think, really?
That's Tim Mendham from Australian Skeptics. That's the show for now. Spacetime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. Spacetime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the Spacetime store for a range of promotional merchandising goodies, or by becoming a Spacetime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Spacetime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to facebook.com/Spacetime with Stuart Gary. And Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.